Let us begin in a place of quiet contemplation. Look around you. Feel the solid ground beneath your feet, the still air on your skin. Observe the objects in the room, each one occupying its own distinct place in the three-dimensional space we call the world. Notice the steady, inexorable, and seemingly universal passage of time, the quiet ticking of a clock that marks the flow of moments from the past, through the present, and into the future. This is the world of our senses. It is a world that is solid, predictable, and deeply reassuring. It is the shape of reality as we experience it, a grand, intuitive architecture that has been the silent, unquestioned backdrop to every human life that has ever been lived. But what if this familiar reality, this solid and reassuring world, is an illusion? What if it is a kind of user interface, a simplified, symbolic representation that has been crafted by our senses and our evolution, not to show us the world as it truly is, but simply to help us survive within it? What if the true shape of reality, the underlying fundamental architecture of existence, is something far stranger, far more beautiful, and far more mysterious than our senses could ever reveal? This journey will be a quiet and gentle descent beneath the surface of the familiar. We will leave the solid ground of our everyday experience and venture into the strange and wonderful landscapes that have been discovered by science in its long and patient quest to understand the nature of everything. We will travel from the vast cosmic scales of the universe to the infinitesimally small granular realm of the quantum, and at every step we will find that the shape of reality is not what it seems. We will learn that space is not an empty stage, but a dynamic, flexible fabric that can be bent and warped. We will discover that time is not a universal clock, but a personal, elastic river that can flow at different rates for different observers. We will encounter a world that is not solid and definite, but is made of shimmering waves of probability, a world where particles can be in many places at once, and where distant, separate objects can be profoundly and mysteriously connected. Our journey will take us to the edge of the observable universe, and we will ask what shape the cosmos itself might have. We will confront the profound mysteries of the dark, unseen substances that sculpt our reality, and we will contemplate the possibility of hidden dimensions, of parallel universes, and of a reality that is a mere holographic projection of a distant two-dimensional surface. This is not a journey that will provide easy answers. It is a journey into the heart of mystery. It is an exploration of the very limits of our human understanding. But it is a journey that is filled with a deep and profound beauty. It is a journey that will replace the comforting certainty of our everyday world with the exhilarating wonder of the unknown. So let us quiet our minds, let us suspend our disbelief, and let us begin our peaceful exploration of the true, hidden, and breathtakingly beautiful shape of reality. Our journey into the shape of reality begins not in the strange modern world of quantum physics or cosmology, but in a place that is far more familiar, a place that is built into the very foundations of our intuition. It is the world as it was first codified and understood by the great mind of Sir Isaac Newton in the 17th century. It is a world of profound simplicity, of absolute certainty, and of a deep clockwork elegance. To understand the revolutions that were to come, we must first spend some time in this classical world to appreciate its beauty, its power, and the deep psychological comfort that it provided to humanity for over 200 years. This is the vision of reality as an empty stage. Let us, in our minds, construct this classical universe. The first and most fundamental element is space. In the Newtonian view, space is absolute. It is a vast, infinite, and unchanging container. It is a three-dimensional Cartesian grid, a silent and featureless backdrop against which the drama of the cosmos unfolds. It is the empty stage. This space is passive. It is inert. It does not act, and it cannot be acted upon. It is simply there, the same everywhere and for all time. The distances between the points on this great cosmic grid are fixed and absolute. A meter is a meter, whether it is here on Earth or in the farthest reaches of the cosmos. It is a universal and unwavering standard of measure. This absolute space provides a fixed, universal frame of reference. It means that we can, in principle, determine the absolute position, the absolute motion, and the absolute rest of any object in the universe. An object is either moving or it is not, and its state of motion is not relative to an observer, but relative to the fixed, invisible structure of space itself. This is a deeply reassuring idea. It gives the universe a sense of solidity, of objective reality. There is a God's eye view, a single, true and unambiguous description of the cosmos. The second fundamental element of this classical world is time. Like space, time in the Newtonian universe is absolute. Newton himself described it as something that flows equably without relation to anything external. It is a great universal river, a single cosmic clock that ticks at the same steady rate for every observer, everywhere in the universe. A second on Earth is precisely the same as a second on Jupiter or on a distant star. The now that we are experiencing is the same now that is being experienced by every other being in the cosmos. This universal simultaneity is a cornerstone of the classical worldview. It means that we can, in principle, create a single, unified timeline of all events in the history of the universe. This absolute space and absolute time are the two independent and unchanging pillars upon which the entire Newtonian edifice is built. They are the stage and the script, the grid and the clock. And upon this stage the great drama of motion takes place, a drama that is governed by a set of simple, elegant and powerful laws. The actors in this drama are the objects, the matter of the universe. In the classical view, matter is made of tiny, solid and indivisible particles, the atoms. These atoms are like tiny, indestructible billiard balls. They have a definite position, a definite momentum and a definite mass. The world is, at its heart, deterministic. If you know the position and the momentum of every single particle in the universe at a single moment in time, and if you know the forces that are acting upon them, you can, in principle, calculate the entire future and the entire past of the cosmos. The universe is a great clockwork machine. It was set in motion at the beginning of time, and it has been unfolding ever since according to a set of fixed and unwavering mathematical laws. There is no room for chance, for ambiguity, or for fundamental uncertainty. The final element of this classical picture is the concept of force, and in particular, the force of gravity. Newton's law of universal gravitation was a triumph of human intellect. It described gravity as a mysterious, invisible force that acts instantaneously across any distance. Every particle of matter in the universe attracts every other particle, with a force that is proportional to the product of their masses, and inversely proportional to the square of the distance between them proportional to the square of the distance between them. This was a strange and radical idea. How could two objects like the Sun and the Earth, which are separated by a vast empty space, exert a force on each other? How could this force know how to act, and how could it travel across the void instantaneously? Newton himself was deeply troubled by this action at a distance, and he famously framed no hypotheses about its underlying cause. He simply described, with breathtaking mathematical precision, how it worked, and it worked beautifully. The Newtonian worldview was a stunning success. It could explain the motion of a falling apple and the orbit of the moon with the same simple set of laws. It could predict the tides, the paths of the comets, and the positions of the planets with incredible accuracy. It was the foundation of the Industrial Revolution, of engineering, and of all of classical physics. It gave humanity a sense of mastery over the natural world. The universe was no longer a place of capricious gods and mysterious spirits. It was a rational, orderly, and knowable place. It was a great cosmic puzzle, and Newton had given us the key to solving it. Let us take a moment to appreciate the deep psychological comfort of this classical worldview. It is a world that is perfectly aligned with our everyday, common-sense intuition. It is a world where objects are solid and have a definite location. It is a world where space is a simple, three-dimensional container. It is a world where time flows at a steady and universal rate for everyone. It is a world that is predictable, that is deterministic, and that is, in principle, completely understandable. The shape of reality in this view is simple, elegant, and absolute. It is a world that makes sense. For over 200 years, this Newtonian picture of reality reigned supreme. It was the bedrock of all science. It seemed to be the final and complete description of the physical world. There were a few small and nagging anomalies, a few tiny cracks in the magnificent facade of the classical edifice. The orbit of the planet Mercury was not behaving quite as it should, and there were strange and puzzling questions about the nature of light and its relationship to space and time. But for the most part, the classical worldview seemed to be unassailable. It was the ultimate truth. But the history of science is a history of revolutions. It is a history of beautiful and comforting ideas being shattered by the relentless and often strange discoveries of observation and experiment. The simple, elegant, and absolute shape of the Newtonian reality, this world of the empty stage and the universal clock, was about to be torn down. And the new reality that would replace it, the reality that would be revealed by the great revolutionary minds of the 20th century, would be a reality that was far stranger, far more complex, and far more beautiful than Newton could ever have imagined. The empty stage was about to become a dynamic and flexible actor in the drama, and the universal clock was about to be shattered into a billion personal and relative timepieces. The journey into the true shape of reality was just beginning. For 2 centuries, the Newtonian universe stood as a monument to human reason, a clockwork cosmos of absolute space and absolute time. It was a world of reassuring certainty. But at the dawn of the 20th century, a young and unassuming patent clerk in Bern, Switzerland, was about to quietly and completely dismantle this entire magnificent edifice. His name was Albert Einstein, and his work would not just refine or adjust the Newtonian picture, it would shatter it and replace it with a vision of reality so strange, so counterintuitive, and so breathtakingly beautiful that it would take the world decades to fully grasp its implications. The revolution began not with a grand pronouncement, but with a simple and elegant thought about the nature of light. The crisis that led to Einstein's revolution had been brewing for some time in the world of physics. The theory of electromagnetism, developed by James Clerk Maxwell in the mid-19th century, had described light as a self-propagating wave of electric and magnetic fields, and Maxwell's equations made a remarkable and puzzling prediction. The speed of light in a vacuum, the famous constant c, was absolute. It was the same for all observers, regardless of their own motion. This was a direct and profound contradiction of the classical Newtonian worldview. In Newton's world, speeds are always relative. If you are driving in a car and you turn on your headlights, you would intuitively expect that the light from your headlights would be travelling faster relative to a stationary observer than the light from a stationary car. But Maxwell's equations said no. The light from both cars would be measured as travelling at the exact same speed, c. This was a deep and irreconcilable paradox. Either Newton's laws of motion were wrong, or Maxwell's laws of electromagnetism were wrong. For years, physicists tried to find a way around this problem, to find a flaw in Maxwell's theory, or to invent a special invisible medium, the luminiferous ether, through which the light waves travelled, and which could serve as a special absolute frame of reference. But all of these attempts failed. Einstein's genius was to take the paradox at face value. He did not try to explain it away. He embraced it. He started with 2 simple postulates. First, the laws of physics are the same for all observers in uniform motion. This is the principle of relativity, an idea that goes all the way back to Galileo. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion. He accepted Maxwell's strange prediction as a fundamental fact of nature, and from these 2 simple ideas, he began to logically and inexorably derive their consequences, and the consequences were world-shattering. If the speed of a light is absolute, then something else, something that we thought was absolute, must be relative. And that something Einstein realized was space and time itself. In a series of papers published in his miracle year of 1905, Einstein unveiled his special theory of relativity, and with it, a new and radical shape of reality. In Einstein's universe, space and time are no longer separate, independent and absolute entities. They are inextricably interwoven into a single, unified, 4-dimensional continuum. He called it Spacetime. This was a profound conceptual leap. The world is not a 3-dimensional stage upon which the drama of time unfolds. The world is a 4-dimensional block, a block universe in which space and time are 2 different but inseparable aspects of the same underlying reality. The 3 dimensions of space and the 1 dimension of time are like the different directions on a map. You can trade one for the other, and in this new 4-dimensional reality, the old Newtonian certainties begin to dissolve. The length of an object, for example, is no longer absolute. An object that is moving at a high speed, relative to an observer, will be measured by that observer as being shorter in the direction of its motion than it would be if it were at rest. This is the phenomenon of length contraction. The faster you go, the more compressed space becomes. Even more shockingly, the passage of time is no longer absolute. A clock that is moving at a high speed relative to an observer will be measured by that observer as ticking more slowly than a stationary clock. This is the phenomenon of time dilation. The faster you go, the slower time flows for you. This is not a mechanical trick or an illusion. It is a fundamental property of time itself. Time is personal. Every observer carries their own personal clock, and the rate at which that clock ticks depends on their motion through space-time. The universal cosmic clock of Newton was shattered into a billion relative and personal timepieces. This led to the famous twin paradox. If one of two twins stays on Earth while the other travels in a spaceship at near the speed of light, when the travelling twin returns, they will be younger than the twin who stayed at home. The travelling twin has literally experienced less time than their sibling. This has been experimentally verified, with incredible precision, using atomic clocks on airplanes and satellites. Time really does slow down when you move. Einstein's special theory of relativity was a stunning achievement, but it was incomplete. It dealt only with observers in uniform motion, moving at a constant speed in a straight line. It did not include the effects of acceleration, or, most importantly, the force of gravity. For the next 10 years, Einstein would wrestle with this problem in what he would later call the most intense and difficult intellectual struggle of his life. And the solution he would eventually find, his general theory of relativity, published in 1915, would be his greatest masterpiece, a theory that would reveal the true and dynamic shape of reality. Einstein's great central insight, the happiest thought of his life, was the principle of equivalence. He realized that the effects of gravity are completely indistinguishable from the effects of acceleration. If you are in a closed elevator that is accelerating upwards in empty space, the feeling of being pushed to the floor is identical to the feeling of the force of gravity. You could perform any experiment you wanted inside that elevator, and you would not be able to tell whether you were in a gravitational field or simply accelerating. From this simple, powerful idea, Einstein made another breathtaking leap. If gravity and acceleration are equivalent, and if acceleration can affect the measurements of space and time, then gravity itself must not be a force in the Newtonian sense at all. Gravity must be a manifestation of the curvature of space-time. This is the heart of the general theory of relativity. Mass and energy do not create a force of gravity. Instead, they tell space-time how to curve, and the curvature of space-time in turn tells mass and energy how to move. The sun does not pull on the Earth with an invisible instantaneous force. Instead, the immense mass of the sun warps the very fabric of space-time around it, creating a great four-dimensional dent or valley in the cosmic geometry. The Earth in its orbit is simply following a straight line, a geodesic, through this curved space-time. It is like a marble rolling around the inside of a large invisible bowl. The marble is not being pulled towards the center by a mysterious force. It is simply following the shape of the surface it is on. The empty, passive, and absolute stage of Newton was gone forever. In its place was a new and dynamic entity, a cosmic fabric that could be bent, stretched, warped, and rippled. The shape of reality was not fixed and eternal. It was a dynamic, evolving, and geometric property of the universe itself, a shape that was constantly being sculpted by the matter and the energy that it contained. Einstein had not just discovered a new law of gravity, he had discovered the true, hidden, and breathtakingly beautiful geometry of the cosmos. The revolution was complete. With the general theory of relativity, Albert Einstein gave humanity a new and profoundly beautiful way to understand the force that governs the cosmos. Gravity, the mysterious and instantaneous action at a distance that had so troubled Newton, was revealed to be something far more intimate and fundamental. It was not a force at all, in the classical sense. It was a consequence of geometry. It was the shape of reality itself. To truly appreciate this conceptual revolution, we must spend some time contemplating this new picture, to visualize the universe not as a collection of objects pulling on each other, but as a landscape of hills and valleys carved into the very fabric of space-time. This is the world of the gravity well. Let us begin with a simple, two-dimensional analogy, a visualization that has become a classic way of explaining Einstein's idea. Imagine that the fabric of spacetime is a large, flat, and stretchy rubber sheet, pulled taut like a trampoline. This flat sheet represents spacetime in the absence of any mass or energy. It is the empty stage of Newton, but now it is a flexible stage. An object moving across this flat sheet will travel in a perfectly straight line. Now, let us place a heavy bowling ball in the center of this rubber sheet. The weight of the ball causes the sheet to bend, to sag, to warp. The bowling ball has created a dent in the fabric, a smooth, curved depression. This depression is the gravity well. The heavy bowling ball represents a massive object, like our sun. The curved, two-dimensional surface of the rubber sheet is an analogy for the four-dimensional curvature of spacetime that the sun creates. Now, let us take a smaller object, a marble, and roll it across the rubber sheet, near the bowling ball. If we roll the marble far away from the bowling ball, where the sheet is still essentially flat, the marble will travel in a straight line, its path unaffected. But if we roll the marble closer to the bowling ball, its path will be deflected. It will be drawn into the curved depression created by the bowling ball. It will begin to circle around the bowling ball following the curved contour of the rubber sheet. It is now in orbit. From the perspective of the marble, it is still moving in the straightest possible line. It is not being pulled by any mysterious force. It is simply following the geometry of the surface it is on. An ant walking on the surface of the rubber sheet would perceive the marble's path as a straight line in its two-dimensional world. But to us, looking down from our three-dimensional perspective, we can see that the marble's path is curved because the surface itself is curved. This is the essence of Einstein's picture of gravity. The Earth is the marble, and the sun is the bowling ball. The Earth is not being pulled by the sun. It is simply following the straightest possible path, a geodesic, through the curved four-dimensional spacetime that the sun has created. The force of gravity is an illusion, an artifact of our limited three-dimensional perception. We feel a force because we are living within a curved geometry. The orbit of the Earth is not a victory of the sun's pulling force over the Earth's desire to fly off in a straight line. It is simply the naturally straight path for an object to follow in the curved landscape of the solar system. This new picture of gravity explained the small, nagging anomaly in the orbit of Mercury that the Newtonian theory could not. Mercury is the closest planet to the Sun, and it is moving in the deepest and most steeply curved part of the Sun's gravity well. Einstein's theory predicted that the orbit of Mercury should precess, meaning the orientation of its elliptical orbit should slowly rotate over time at a rate that was slightly different from the Newtonian prediction. And when the calculations were done, Einstein's theory predicted the precession of Mercury's orbit with perfect accuracy. It was the first stunning confirmation of his new and radical idea. The curvature of space-time does not just affect the motion of massive objects like planets, it also affects the motion of massless particles like photons of light. In the classical Newtonian view, light should not be affected by gravity because it has no mass. But in Einstein's view, light, like everything else, must travel through space-time, and if space-time is curved, then the path of light must also be curved. Einstein predicted that the light from a distant star passing close to the Sun should be bent by the Sun's gravity well. This was a radical and testable prediction. The only way to observe this effect would be during a total solar eclipse, when the bright light of the Sun is blocked out and the stars near the Sun become visible. In 1919, the British astronomer Sir Arthur Eddington led an expedition to observe a solar eclipse from the island of Principe, off the coast of Africa. They took photographs of the stars near the Sun during the eclipse and compared them to photographs of the same stars, taken at a different time of year, and they found that the positions of the stars had indeed been shifted. The starlight had been bent by the exact amount that Einstein's theory had predicted. This was a moment of profound triumph. The news was reported in newspapers around the world. Einstein became an international celebrity overnight. The obscure patent clerk had redrawn the map of the cosmos. The universe was not a clockwork machine. It was a dynamic, geometric landscape. The concept of the gravity well allows us to visualize the entire universe as a vast, undulating landscape of hills and valleys. Every object with mass, from a planet to a star to a galaxy, creates its own dent in the fabric of space-time. A galaxy is a great, deep and complex valley, with smaller valleys within it for each of the billions of stars it contains. A cluster of galaxies is a vast, sprawling mountain range of space-time curvature, and the motion of everything in the universe is simply the story of objects rolling and falling along the contours of this great cosmic landscape. This picture also gives us a new and intuitive way to understand the escape velocity of a planet. To escape from the Earth's gravity, a rocket must have enough energy to climb all the way up and out of the Earth's gravity well and to reach the flat space-time beyond. The deeper the gravity well, the more massive the planet, the more energy is required, and the higher the escape velocity. And this leads us to the most extreme and fascinating objects in the universe, the black holes. A black hole is an object whose mass is so great, and whose gravity well is so deep and so steep, that the escape velocity exceeds the speed of light. The gravity well is no longer a well, it is a bottomless pit. The curvature of space-time has become so extreme that it has, in a sense, torn a hole in the fabric of reality. Once anything, even light, crosses the boundary of this pit, the event horizon, it can never escape. It is destined to fall forever towards the central singularity, the point of infinite density and infinite curvature. To contemplate the world as a landscape of gravity wells is to undergo a profound shift in our perception of reality. It is to see that the forces that govern our lives are not mysterious, invisible tendrils reaching across the void. They are the very shape of the world we inhabit. We are living, moving, and having our being within a great, unseen, and beautiful geometry. The force we feel, the weight that holds us to the earth, is the gentle, persistent, and intimate embrace of a curved and loving cosmos. Of all the revolutionary ideas that Albert Einstein unleashed upon the world, none is more profound, more personal, or more deeply unsettling to our intuition than his revelation about the nature of time. In the classical Newtonian world, time was a great universal river, a cosmic metronome that ticked at the same, steady rate for everyone and everything in the universe. It was the absolute and unchanging backdrop to all of existence. But Einstein's theories of relativity shattered this comforting illusion. They revealed that time is not a rigid, external entity. It is a malleable, personal, and elastic property of the universe. Time can be stretched and compressed. It can flow at different rates for different observers. The secret of the clock is that every clock tells its own unique time. Let us first return to the special theory of relativity and the strange consequences of the absolute speed of light. Einstein showed that if the speed of light is the same for all observers, then time itself must be relative. The faster you move through space, the slower you move through time. This is the phenomenon of time dilation. Imagine two observers. One is standing still on a train platform. The other is on a train that is moving past at a very high speed, close to the speed of light. The observer on the train has a special light clock. It consists of two mirrors, one on the floor and one on the ceiling of the train car, and a single photon of light that is bouncing back and forth between them. Each time the photon hits a mirror, the clock ticks. From the perspective of the observer on the train, the photon is simply travelling straight up and down, a fixed and constant distance. The ticks of their clock are regular and steady. But now, let us consider the perspective of the stationary observer on the platform as they watch the train and its light clock go by. From their point of view, the photon is not travelling straight up and down. Because the train is moving, the photon must travel a longer diagonal path to get from the floor to the ceiling and back again. Now, we come to the crucial point. Both observers, according to Einstein's second postulate, must measure the speed of that single photon as being the exact same speed, the speed of light, c. If the stationary observer sees the photon travelling a longer distance, but measures its speed as being the same, then there is only one possible conclusion, as strange as it may seem. The stationary observer must also see the moving clock as taking more time to complete a single tick. From the perspective of the platform, the clock on the train is running slow. Time itself for the moving observer has slowed down. This is not a trick of perception or a mechanical failure of the clock. It is a fundamental feature of the geometry of space-time. When you are at rest, you are travelling purely through the time dimension. All of your motion is motion through time, but when you begin to move through the spatial dimensions, you must borrow some of your motion from the time dimension. Your total combined speed through the 4 dimensions of space-time is always the speed of light. So, The faster you move through space, the less speed you have available for your journey through time. Your personal clock, the rate at which you experience the passage of time, slows down. This effect is real. It has been measured with incredible precision. The atomic clocks on the GPS satellites that orbit the Earth are moving at a high speed relative to us on the ground. As a result, their clocks run slightly slower than our clocks, by about 7 microseconds every day. If the engineers who designed the GPS system did not account for this relativistic time dilation, the entire system would fail within minutes, accumulating navigational errors of several kilometers every day. Your ability to find your way with your smartphone is a daily, practical confirmation of the strange, elastic nature of time. But the story gets even stranger. Einstein's general theory of relativity, his theory of gravity, revealed that it is not just motion that can affect the flow of time. Gravity itself can slow down time. This is the phenomenon of gravitational time dilation. Let us return to our image of the gravity well. A massive object like the Earth creates a dent in the fabric of space-time. The general theory of relativity predicts that the deeper you are in this gravity well, the slower time will flow. A clock at sea level, which is closer to the center of the Earth and deeper in its gravity well, will tick more slowly than a clock on top of a mountain. We can visualize this by imagining that the fabric of space-time is not just a spatial grid, but a temporal one as well. The presence of a massive object stretches the time dimension in its vicinity. The ticks of a clock are like the markings on a ruler. In the flat space-time of empty space, the markings are evenly spaced. But near a massive object, the ruler of time is stretched out. The markings are farther apart. It takes longer to get from one tick to the next. This effect is also real, and it has also been measured. In a famous experiment conducted in 1959 by Pound and Rebka, scientists used the incredibly precise frequency of gamma rays to measure the difference in the rate of time flow between the basement and the top floor of a laboratory building at Harvard University. They found that the clock in the basement, which was closer to the center of the Earth, was indeed running slightly slower than the clock on the top floor, by the exact amount that Einstein's theory had predicted. The effect is even more pronounced for the GPS satellites. In addition to the effect of their high speed, the satellites are also in a much weaker gravitational field than we are on the surface. They're higher up in the Earth's gravity well. This means that their clocks run faster than ours, by about 45 microseconds every day. When you combine this with the 7 microsecond slowing due to their speed, the net effect is that the GPS clocks run faster than ground clocks by about 38 microseconds per day. This gravitational time dilation must also be constantly corrected for the system to work. The implications of this are profound and deeply personal. Every one of us is living in our own, unique time stream. A person who lives their entire life in a high-rise apartment will age, ever so slightly, faster than a person who lives in a bungalow by the sea. Your head is aging faster than your feet. The difference is, of course, infinitesimally small in our everyday lives, but it is real. The universal absolute river of time has been shattered into an infinite number of personal, local streams, each one flowing at a slightly different rate, its pace dictated by the local curvature of space-time. This leads us to a new and strange understanding of the shape of reality. The now that we experience is not a universal, simultaneous moment that is shared by everyone in the cosmos. The very concept of simultaneity is relative. Two events that appear to happen at the same time for one observer may appear to happen at different times for another observer who's in a different state of motion or in a different gravitational field. This suggests a picture of the universe that is often called the block universe. In this view, the past, the present, and the future are all equally real. The entire history of the universe, from the Big Bang to the distant future, exists as a single, timeless, four-dimensional block of space-time. The flow of time, our powerful and persistent feeling that the present moment is constantly moving forward, is an illusion, a feature of our human consciousness, not a fundamental property of the physical world. The block is static. It does not happen. It simply is. We, in our conscious experience, are simply illuminating a sequence of slices of this block, creating the illusion of a moving present. To contemplate the relativity of time is to be confronted with the profound and beautiful strangeness of the universe. It is to let go of one of our most deeply held intuitions, and to embrace a reality that is far more fluid, more personal, and more mysterious than we ever imagined. It is to understand that the steady ticking clock on the wall is not a measure of some absolute external reality. It is a local, provincial, and deeply personal affair. The secret of the clock is that it is not telling the time of the universe. It is only telling the time of here and of now. Our journey into the shape of reality has so far taken us through the vast, curved, and continuous landscapes of Einstein's relativity. It is a world of smooth fabrics, of flowing rivers of time, and of elegant geometric certainty. But in the early decades of the 20th century, at the same time that Einstein was developing his grand cosmic theories, another even stranger revolution was beginning to take place. This was a revolution that would explore not the infinitely large, but the infinitesimally small. It was a journey into the heart of matter and of energy, a journey into the quantum realm. And the shape of reality that it would reveal would be a world that was not smooth, not continuous, and not certain. It would be a world of jumps, of packets, and of fundamental, irreducible graininess. It would be a world of pixels. The story of the quantum leap begins in the year 1900 with the German physicist Max Planck. Planck was working on a puzzle known as the black-body radiation problem. A black body is an idealized object that absorbs all of the radiation that falls on it. When it is heated, it emits radiation of its own, across a spectrum of wavelengths. The classical physics of the time, which treated energy as a continuous wave-like phenomenon, made a prediction about this spectrum that was spectacularly wrong. It predicted that a black body should emit an infinite amount of energy at the short ultraviolet wavelengths, a result that was so absurd it became known as the ultraviolet catastrophe. Planck struggled with this problem for years, and then, in what he would later call an act of desperation, he tried a radical and seemingly nonsensical new idea. He decided to abandon the centuries-old assumption that energy was continuous. He proposed that energy could not be emitted or absorbed in any arbitrary amount. Instead, he suggested, it could only be emitted or absorbed in discrete indivisible packets, like a kind of atom of energy. He called these packets quanta. The energy of a single quantum, he proposed, was proportional to the frequency of the radiation. This was a bizarre and revolutionary idea. It was like saying that you could not fill a glass of water to any level you wanted, but could only add water in discrete 1-ounce packets. It went against all of the classical intuition about the smooth, continuous nature of the world. Planck himself was deeply unsettled by his own idea, and did not fully believe it. He saw it as a mathematical trick, a temporary fix that would hopefully be replaced by a more sensible classical explanation. But the trick worked. By assuming that energy was quantized, Planck was able to derive a new equation that perfectly described the observed spectrum of black-body radiation. The ultraviolet catastrophe was averted. The quantization of energy prevented the emission of an infinite amount of high-frequency radiation. 5 years later, in the same miracle year that he published his theory of special relativity, Albert Einstein took Planck's radical idea one giant step further. Einstein was working on another puzzle, the photoelectric effect. It had been observed that when light shines on a metal surface, it can knock electrons out of the metal. But the way this happened was strange. The classical wave theory of light predicted that a brighter light, a wave with a higher amplitude, should knock out electrons with more energy. But this is not what was observed. A brighter light knocked out more electrons, but the energy of each individual electron was the same. The energy of the electrons depended only on the frequency, or the color of the light. A blue light would knock out higher energy electrons than a red light, no matter how bright the red light was. Einstein realized that Planck's quantum hypothesis could explain this perfectly. He proposed that light itself is not a continuous wave, but is composed of a stream of these discrete particle-like packets of energy. He called these packets photons. The energy of each photon is determined by its frequency. When a photon strikes the metal, it transfers all of its energy to a single electron. A brighter light is simply a stream with more photons, so it knocks out more electrons. But the energy of each electron is determined by the energy of the single photon that hit it, which in turn is determined by the frequency of the light. This was an even more radical idea than Planck's. Planck had only said that energy was quantized at the moment of its emission or absorption. Einstein was saying that light itself, the very stuff of reality, is fundamentally granular. It is made of particles. This idea of the light quantum was so strange that it was rejected by the physics community for years. Even Planck was skeptical. But over time, the experimental evidence became undeniable. The quantum nature of light was a fact. This was the beginning of the quantum revolution. Over the next few decades, a new generation of physicists, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others, would build on these ideas and develop a complete and powerful new theory of the subatomic world, quantum mechanics. And at every turn they would find that the world at its most fundamental level is quantized. They discovered that it is not just energy that is quantized. The properties of matter are also quantized. An electron orbiting an atom, for example, cannot have any arbitrary amount of energy. It can only exist in certain, discrete, and allowed energy levels, like the rungs of a ladder. It can jump from one level to another by absorbing or emitting a photon of the exact right amount of energy, but it can never exist in the space between the rungs. This is the quantum leap. Other properties, like the spin of a particle, are also quantized. A particle's spin is a kind of intrinsic angular momentum, but it can only have certain discrete values. It can be spin up or spin down, but never anything in between. The very fabric of reality, at its smallest and most fundamental scale, seems to be pixelated. It is not a smooth, continuous, and infinitely divisible substance. It is built out of discrete, indivisible, and fundamental units. There is a smallest possible packet of energy, a smallest possible unit of action, a smallest possible pixel of reality. This is a profound and deeply counterintuitive shift in our understanding of the shape of reality. Our senses, and the classical physics that is built upon them, give us a world that is smooth and continuous. We can imagine dividing a line in half, and then in half again, forever. We can imagine a car smoothly accelerating from one speed to another, but the quantum world tells us that this is an illusion, an artifact of our large scale. At the bottom, there is a fundamental graininess, a granularity that we can never get past. To contemplate this quantum leap is to see the world with new eyes. It is to look at a beam of sunlight and to see not a continuous wave, but a stream of a billion tiny particle-like photons. It is to look at a solid object and to understand that the electrons within its atoms are not orbiting like tiny planets, but are locked into a rigid, quantized ladder of energy levels. It is to accept that the smooth, seamless world of our everyday experience is a macroscopic illusion, and that the true, underlying shape of reality is a world of discrete steps, of indivisible packets, and of beautiful, fundamental and irreducible pixels. The universe is not a painting, it is a mosaic. The quantum revolution began with the startling discovery that the world at its most fundamental level is pixelated. Energy, light, and the properties of matter all come in discrete, indivisible packets, or quanta. This idea, as strange as it was, could have been incorporated with some difficulty into a modified classical worldview. We could have simply imagined the world as being made of tiny, indestructible, point-like particles that just happen to have quantized properties. The universe would still be a clockwork machine, but a machine made of very small, discrete parts. But the quantum world had a far deeper, stranger, and more profound secret to reveal. A secret that would shatter not just our picture of the world's substance, but our very concept of what it means for something to be real. This is the secret of the wave-particle duality, the central and enduring mystery of the quantum realm. The story begins, once again, with light. For centuries there had been a debate about the nature of light. Newton had argued that light was a stream of particles, or corpuscles. His contemporary Christian Huygens had argued that light was a wave. By the 19th century, the wave theory had won a decisive victory. Experiments showing the diffraction and the interference of light seemed to prove, beyond any doubt, that light was a wave. But then, as we have seen, Einstein's explanation of the photoelectric effect showed that light must also be a particle, a photon. So which is it? Is light a wave, or is it a particle? The astonishing and deeply unsettling answer of quantum mechanics is that it is both. Let us try to visualize this with the famous double-slit experiment, an experiment that the physicist Richard Feynman called the heart of quantum mechanics. Imagine a barrier with two thin, parallel slits in it. We are going to fire something at this barrier. First, let us fire a stream of tiny solid particles like marbles. Some of the marbles will be blocked by the barrier, some will go through the left slit and some will go through the right slit. If we place a detector, screen on the other side, we will find two distinct bands of hits, one behind each slit. This is simple, classical particle behavior. Now, let us try the same experiment with a wave, like a water wave. When the wave hits the barrier, it will pass through both slits at the same time. The two new waves that emerge from the slits will then interfere with each other. Where the crest of one wave meets the crest of another, they will reinforce each other, creating a larger wave. Where the crest of one wave meets the trough of another, they will cancel each other out. The result on the detector screen will be a characteristic interference pattern, a series of alternating bright and dark bands showing the places where the waves have added up and where they have cancelled out. This is simple, classical wave behavior. Now for the quantum mystery. Let us fire a stream of electrons at the two slits. An electron, we have always been taught, is a tiny particle-like constituent of matter, so we would expect to see the same result as we did with the marbles, two distinct bands on the screen. But this is not what we see. Incredibly, we see an interference pattern. The electrons which we thought were particles are behaving like waves. They seem to be passing through both slits at once and interfering with themselves. This is already deeply strange, but it gets stranger. What if we try to outsmart the electrons? What if we place a detector at the slits to see which slit each individual electron is going through? We turn on our detector, and we fire the electrons one at a time. Now we can see for each electron whether it went through the left slit or the right slit. It is behaving like a good, classical particle. But when we look at the pattern that builds up on the screen behind the slits, the interference pattern has vanished. We are back to the two simple bands that we saw with the marbles. The very act of observing which path the electron took has forced it to choose a path, to behave like a particle, and has destroyed its wave-like behavior. This is the profound and inescapable mystery of the quantum world. The fundamental constituents of reality, the electrons, the photons, the quarks, are not in their essence either particles or waves. They are something else, something for which we have no classical analogy. They are a strange hybrid entity that will reveal its particle-like nature or its wave-like nature depending on how we choose to observe it. The great physicist Erwin Schrödinger tried to capture this strange duality with a mathematical tool that has become the cornerstone of quantum mechanics, the wave function. The wave function is a mathematical description of a quantum system, like an electron. But it does not describe the electron as a particle with a definite position. Instead, it describes the electron as a wave of probability. The wave function spreads out through space, and the height, or the amplitude of the wave at any given point corresponds to the probability of finding the electron at that point if we were to look for it. Before we make an observation, the electron does not have a definite position. It is not a tiny solid ball that is hiding somewhere in the cloud of probability. The cloud is the electron. The electron exists in a superposition of all of its possible states at once. It is in a sense everywhere and nowhere. It is a shimmering, ghostly wave of pure potentiality. Then, when we make an observation, when we interact with the system in a way that forces it to reveal its position, something remarkable happens. The wave function collapses. The cloud of probability instantly vanishes, and the electron appears, as if by magic, at a single, definite location. The act of observation has transformed the ghostly wave of potentiality into a solid, particle-like reality. This is a profound and deeply philosophical shift in our understanding of the shape of reality. The classical world was a world of certainty, of definite properties. An object had a position, whether we were looking at it or not. The moon is still there, even when we close our eyes. But the quantum world is a world of fundamental, irreducible uncertainty and probability. An electron does not have a definite position until we measure it. Before the measurement, its position is not just unknown, it is undefined. The reality of the electron is created, in a sense, by the act of our observation. This is the essence of Werner Heisenberg's famous uncertainty principle. It states that there are certain, complementary pairs of properties, like the position and the momentum of a particle, that we can never know with perfect accuracy at the same time. The more precisely you measure the position of an electron, the less precisely you can know its momentum, and vice versa. This is not a limitation of our measuring instruments, it is a fundamental, built-in feature of reality itself. The very concept of a particle, having both a definite position and a definite momentum at the same time, is meaningless in the quantum world. To contemplate this wave of probability is to let go of our most deeply held, classical intuitions about the nature of existence. It is to accept that the world, at its most fundamental level, is not a collection of solid, definite objects. It is a shimmering, probabilistic, and deeply mysterious dance of potentiality and actuality. The shape of reality is not a fixed and solid sculpture. It is a cloud, a wave, a ghost. It is a world that is constantly waiting, in a state of suspended quantum animation, for the touch of an observer to call it into being. The solid world we see around us is the result of a billion constant and instantaneous collapses of these ghostly waves of probability. The shape of reality is not something that is given. It is something that is constantly being chosen. The quantum world has so far revealed itself to be a place of profound strangeness, a world of pixelated reality and shimmering waves of probability. It has forced us to abandon our classical notions of certainty and of definite properties, but it has saved its most radical, most mind-bending and most spooky revelation for last. This is the phenomenon of quantum entanglement, a strange and intimate connection between particles that seems to violate our most deeply held intuitions about space, about distance, and about the very nature of reality itself. It is a phenomenon that so troubled Albert Einstein that he famously dismissed it as spooky action at a distance, and it is a phenomenon that reveals that the shape of reality is not just uncertain, it is profoundly and mysteriously non-local. Let us imagine a process that creates a pair of entangled particles, say, 2 electrons. These 2 electrons are created in such a way that their spin properties are correlated. As we have seen, spin is a quantized property. An electron can be either spin up or spin down. Our entangled pair is created with a total spin of 0. This means that if one of the electrons is spin up, the other one must be spin down, and vice versa. Their fates are linked. They are a single, unified quantum system, described by a single wave function. Now, let us separate these 2 entangled electrons. We send one to a laboratory in New York, and the other to a laboratory in Geneva. They are now thousands of miles apart. According to the principles of quantum mechanics, before we make a measurement, neither electron has a definite spin. Each one is in a superposition of both spin up and spin down. The combined system is in a state of spin up/spin down and spin down/spin up at the same time. Now the observer in New York decides to measure the spin of their electron. They perform the measurement, and they find that their electron is, say, spin up. The wave function has collapsed. The electron has been forced to choose a definite state. But here is the spooky part. In the exact same instant that the measurement is made in New York, the wave function of the entire 2-particle system collapses, and the electron in Geneva, thousands of miles away, instantly chooses the opposite state. It becomes spin down. The observer in Geneva can perform their own measurement, and they will find, with 100% certainty, that their electron is spin down. It is as if the electron in Geneva knew instantaneously that its partner in New York had been measured and had been found to be spin up. This connection, this transfer of information, seems to happen faster than the speed of light. It seems to violate Einstein's own sacred speed limit, the cosmic law that nothing can travel faster than light. This is the spooky action at a distance that so disturbed Einstein. He, along with his colleagues Boris Podolsky and Nathan Rosen, in what became known as the EPR paradox, argued that this was a sign that quantum mechanics must be an incomplete theory. They argued that the correlation between the 2 particles must have been predetermined from the moment they were created. They proposed that each particle must be carrying some kind of hidden, internal instruction set, some hidden variables, that told it which way to spin when it was measured. The correlation was not a spooky, faster-than-light connection. It was a classical, pre-existing correlation, like wearing 2 different coloured gloves from a pair. If you find that you are wearing the left-handed glove, you know instantly that the other glove, no matter how far away it is, must be the right-handed one. There is no spooky action, just a pre-existing hidden property. For decades, this was a philosophical debate. There seemed to be no way to experimentally distinguish between the spooky action of quantum mechanics and the hidden variables of Einstein. But then, in the 1960s, the physicist John Bell devised a brilliant theoretical test, a mathematical inequality that could, in principle, be tested in a laboratory. Bell's theorem showed that if the world was governed by local hidden variables, as Einstein believed, then the results of a certain kind of measurement on entangled particles would have to obey a certain statistical limit. But if the world was governed by the strange, non-local connections of quantum mechanics, then this limit could be violated. It took many years to develop the technology to perform Bell's test with sufficient precision. But in the 1980s, and with increasing accuracy ever since, a series of brilliant experiments, most notably by the physicist Alain Aspect, have been performed, and the results are in, and they are unambiguous. The universe violates Bell's inequality. Einstein was wrong. The spooky action at a distance is real. This is a profound and deeply unsettling conclusion. It means that our universe is fundamentally non-local. The shape of reality is not a collection of separate, independent objects that only interact with their immediate surroundings. It is a single, interconnected and holistic entity. The two entangled electrons, even when they are separated by thousands of miles, are not two separate objects. They are, in some deep and mysterious way, still a single, unified system. The space between them does not seem to exist. It is important to understand that this non-local connection cannot be used to send information faster than light. The observer in New York cannot use their measurement to send a message to the observer in Geneva. The result of the measurement in New York is completely random. They are equally likely to find spin up or spin down. They cannot control the outcome, and so they cannot use it to encode a message. The correlation only becomes apparent after the two observers have brought their results together and compared them. The spooky connection respects the cosmic speed limit when it comes to communication, but it reveals a deeper, hidden, and instantaneous connectivity in the fabric of reality itself. To contemplate the entangled dance is to be confronted with the ultimate mystery of the quantum world. It is to accept that the universe is not a collection of separate parts, but a single, indivisible whole. It is to see that the space that separates us, the vast empty distances between the stars and the galaxies, may be in some deep and fundamental way an illusion. The shape of reality is not a local affair. It is a holistic, interconnected, and profoundly unified web of relationships. Every particle in the universe may be in some way connected to every other particle, a silent, invisible, and instantaneous dance of spooky quantum connection that has been going on since the very beginning of time. The universe is not a collection of things. It is a single, great, and entangled thought. Our journey into the shape of reality has taken us from the strangely flexible fabric of space-time to the bizarre, probabilistic, and interconnected world of the quantum. We have explored the very small. Now let us pull our perspective back, far back, to the largest possible scales. Let us look not at the space between atoms, but at the vast cosmic ocean of the galaxies. Here too, in the immense dark silence of the cosmos, we will find that our perception of reality is bounded, that our vision is finite, and that we are living inside a vast, spherical, and inescapable horizon. This is the cosmic horizon, the ultimate edge of the observable universe. To understand this horizon, we must first recall two fundamental facts about our universe. The first is that the universe has a finite age. The best evidence we have from a multitude of different and converging lines of inquiry tells us that our universe began approximately 13.8 billion years ago in a hot, dense and rapidly expanding state that we call the Big Bang. The second fact is that the speed of light, the cosmic speed limit, is finite. Light travels incredibly fast, but it does not travel instantaneously. It takes time for the light from a distant object to reach us. These two simple facts, when put together, lead to a profound and inescapable conclusion. There is a limit to how far we can see. Since the universe is 13.8 billion years old, we can only see the objects whose light has had 13.8 billion years, or less, to reach us. Any object that is farther away than that, any object whose light would have taken longer than 13.8 billion years to get here, is, for now, completely invisible to us. Its light has simply not had enough time to complete the journey. This creates a horizon around us, a spherical boundary that separates the part of the universe that we can see from the part that we cannot. This is the cosmic light horizon, or the observable universe. It is a sphere, with us, the observer, at its centre. The edge of this sphere is the most distant and the most ancient thing we can possibly see. When we look at an object that is on our cosmic horizon, we are not seeing it as it is today. We are seeing it as it was 13.8 billion years ago, in the fiery infant moments of the cosmos. The light from that object has been travelling across the expanding universe for the entire age of the universe to reach our telescopes today. It is important to understand what this horizon is and what it is not. It is not a physical barrier. It is not a wall at the edge of space. It is a horizon of information, a horizon of light. An observer in a distant galaxy would have their own personal cosmic horizon, their own spherical bubble of observation centered on them. Their observable universe would overlap with ours, but they would be able to see parts of the cosmos that are, for us, beyond our horizon, and we can see parts that are beyond theirs. The size of the observable universe is not simply 13.8 billion light-years in radius. This is a common misconception. We must also account for the fact that the universe itself has been expanding during the 13.8 billion years that the light has been travelling. The distant galaxy that emitted the light we are seeing today was much closer to us when it emitted that light. But in the intervening eons, the space between us and that galaxy has stretched dramatically. When we factor in this cosmic expansion, the current, proper distance to the edge of our observable universe is estimated to be about 46.5 billion light-years in any direction. This means that the entire observable universe is a sphere with a diameter of about 93 billion light-years. This is a number of almost incomprehensible scale, but as vast as it is still finite. Our view of reality is fundamentally limited. We are living inside a bubble. And this leads to one of the most profound and tantalizing questions in all of science. What lies beyond the horizon? The honest answer is that we do not know, and we may never know for sure. We have no way to directly observe it. But our best theories, and the evidence we have from the part of the universe that we can see, give us some compelling and beautiful ideas. The simplest and most widely accepted assumption is that the universe beyond our horizon is, on the large scales, pretty much the same as the universe within our horizon. It is filled with the same kinds of galaxies, the same kinds of stars, and the same fundamental laws of physics. This is the cosmological principle, the idea that the universe is on average homogeneous and isotropic, the same in all locations and in all directions. If this is true, then the universe as a whole, the entire universe, is vastly, perhaps infinitely, larger than the small finite part that we can see. Our 93 billion light-year bubble of observation is just a tiny, insignificant speck in a much grander and perhaps eternal cosmic ocean. This idea has a strange and wonderful consequence. If the universe is indeed infinitely large, and if it is filled with a finite number of possible quantum states, then any possible arrangement of matter and energy must eventually repeat itself. This means that if you travel far enough in any direction, you will eventually encounter another region of the cosmos that is identical to our own observable universe. You will find another galaxy that is identical to our Milky Way, another star that is identical to our Sun, and another planet that is identical to our Earth. And on that planet there will be a person who is identical to you, reading these exact same words. In an infinite universe, every possible story is not just told, but is told an infinite number of times. But there are other, more exotic possibilities for what lies beyond our horizon. The theory of cosmic inflation, which is our leading model for the very first moments of the Big Bang, suggests that our universe may be just one bubble in a much larger, eternally inflating multiverse. In this picture, the fabric of space-time is constantly and rapidly expanding, and every now and then, a small patch of it will slow down and decay into a new stable universe, like a bubble forming in a pot of boiling water. Our entire observable universe, and even the vast infinite space beyond our horizon, may be just one of these bubbles. And there may be an infinite number of other disconnected bubble universes, each with its own unique physical laws, its own unique dimensions, and its own unique story. To contemplate the cosmic horizon is to be confronted with the profound and humbling limits of our own human perspective. It is to realize that the reality we can see is not the whole of reality. We are like ancient island-dwelling mariners whose entire world was bounded by the circle of the sea horizon. We can see the ships that are within our horizon, but we can only guess at the vast unseen continents and the strange new worlds that may lie beyond it. The cosmic horizon is the ultimate boundary, the final veil. It separates the known from the unknowable, but it is also a source of deep and profound wonder. It is a reminder that the universe is almost certainly far grander, far stranger, and far more magnificent than our limited, finite minds can ever fully comprehend. The shape of our reality is a bubble, and the greatest mystery of all is the vast, dark, and silent ocean in which that bubble floats. We have discovered that our view of the universe is finite, bounded by a cosmic horizon. But what of the universe itself? What is the overall shape, the global geometry, of the entire four-dimensional spacetime in which we live? Is it, like the universe of Newton, an infinite, flat, and Euclidean space? Or does it have a grand, cosmic curvature, a shape that is determined by the very substance of its own being? This is one of the most fundamental and long-standing questions in all of cosmology. And the answer, according to Einstein's general theory of relativity, depends on a single, crucial parameter, the total density of all the mass and all the energy contained within the universe. Einstein's theory tells us that mass and energy curve space-time. It therefore follows that the overall shape of the entire universe must be determined by the total amount of stuff that it contains. There is a certain critical density. If the actual density of the universe is greater than this critical density, then there is enough mass and energy to cause the universe to curve back on itself into a closed geometry. If the actual density is less than the critical density, then there is not enough mass to halt the universe's expansion, and it will have an open geometry. And if the actual density is exactly equal to the critical density, then the universe will be perfectly flat. Let us try to visualize these three possible shapes of our reality. First, let us consider a closed universe. In a closed universe, the density of mass and energy is high enough that the collective gravity is strong enough to bend space-time into a shape that is analogous to the surface of a sphere. This is a four-dimensional hypersphere, a shape that is impossible for our three-dimensional minds to visualize directly, but we can use the two-dimensional analogy of the surface of the Earth. The surface of the Earth is a finite two-dimensional space, but it has no boundary and no edge. If you start walking in a straight line in any direction, you will never fall off the edge. You will simply, eventually, return to your starting point. A closed, hyperspherical universe is like this. It is finite in volume, but it has no boundary. If you could travel in a spaceship in a perfectly straight line for a long enough time, you would eventually and astonishingly arrive back where you started. In a closed universe, the normal rules of Euclidean geometry do not apply. The sum of the angles in a large cosmic triangle would be more than 180 degrees. Two parallel lines, if extended far enough, would eventually converge and cross. The fate of a closed universe is also dramatic. The immense gravity that closes the universe would eventually halt its expansion and cause it to begin to recollapse, leading to a final, fiery, big crunch, a sort of Big Bang in reverse. Now, let us consider an open universe. This occurs if the density of the universe is less than the critical density. In this case, there is not enough gravity to bend the universe back on itself. The shape of an open universe is analogous to the surface of a saddle, a hyperbolic geometry that curves away from itself at every point. An open universe is infinite in extent. If you travel in a straight line, you will travel forever, never returning to your starting point. The rules of geometry are also different here. The sum of the angles in a large triangle would be less than 180 degrees. Two parallel lines would diverge, getting farther and farther apart. The fate of an open universe is to expand forever, becoming colder, darker, and emptier as time goes on. Finally, let us consider the flat universe. This is the special Goldilocks case, where the density of the universe is exactly equal to the critical density. In this case, the universe is perfectly balanced. The geometry is the familiar Euclidean geometry that we learn in school. The sum of the angles in a triangle is exactly 180 degrees. Parallel lines remain parallel forever. A flat universe, like an open universe, is infinite in extent and will expand forever, though the rate of expansion will slow down over time, approaching zero. So, which of these three shapes does our own universe have? Is our reality closed, open, or flat? This is a question that can be answered, in principle, by observation. For decades, cosmologists have been trying to measure the geometry of our universe and to take a census of its total mass and energy content. One of the most powerful ways to measure the geometry of the universe is to look at the oldest light we can see, the cosmic microwave background, CMB. The CMB is the faint afterglow of the Big Bang, a thermal radiation that fills the entire sky. It is a snapshot of the universe as it was only 380,000 years after the Big Bang. This ancient light is not perfectly uniform. It is filled with tiny random fluctuations in temperature, tiny hot spots and cold spots that were the seeds of all the future structure in the universe. The physical size of these spots at the time the CMB was emitted is something that we can calculate with great precision from our understanding of the physics of the early universe. We know how big they should be. We can then measure the apparent angular size of these spots as we see them in the sky today. The geometry of the universe, the shape of the space through which this ancient light has been travelling for 13.8 billion years, will act like a giant cosmic lens. If the universe is closed, its positive curvature will act like a magnifying lens, and the spots in the CMB will appear larger than they should. If the universe is open, its negative curvature will act like a demagnifying lens, and the spots will appear smaller. And if the universe is flat, the light will travel in straight lines, and the spots will appear to be their true, calculated size. Over the past 2 decades, a series of incredibly precise satellite missions, most notably the WMAP and the Planck satellites, have mapped these tiny fluctuations in the CMB with breathtaking accuracy. And the result is in. The data shows, with a very high degree of confidence, that the spots are the size they should be. The geometry of our observable universe is, to within the limits of our measurement, perfectly flat. This is a stunning and deeply puzzling result. The flat geometry is a very special, very unstable, and very unlikely state. It is like balancing a pencil on its point. Any tiny deviation from perfect flatness in the early universe should have been magnified exponentially by the subsequent cosmic expansion. For the universe to be so perfectly flat today, it must have been born with a density that was exquisitely, almost supernaturally, fine-tuned to the critical density, to an accuracy of 1 part in 10 to the power of 60. This is the flatness problem, one of the great unsolved mysteries of modern cosmology. The theory of cosmic inflation offers a potential solution to this problem. Inflation proposes that in the very first, fleeting fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated exponential expansion, growing from a subatomic size to a macroscopic size almost instantaneously. This incredible stretching would have had the effect of flattening any initial curvature that the universe might have had, in the same way that inflating a tiny wrinkled balloon to the size of the Earth would make its surface appear perfectly flat to any small observer living on it. Inflation naturally produces a universe that is vast, and that is very, very close to being perfectly flat. To contemplate the shape of the universe is to be confronted with the grand cosmic consequences of Einstein's vision. The fate of our reality, the very nature of its geometry, is a story that is written in the language of density, of curvature, and of expansion. And the story that our universe is telling us is a strange and beautiful one. It is the story of a reality that is balanced on a knife's edge, a reality that is, against all odds, perfectly, beautifully, and mysteriously flat. Our journey has led us to a remarkable conclusion. The universe, on the larger scales, appears to be perfectly flat. This flatness implies that the total density of all the mass and all the energy in the cosmos must be exquisitely balanced at a specific critical value. It is a universe that is poised on a knife's edge. This discovery, as profound as it is, immediately presents us with a new and even deeper mystery. When we take a census of all the stuff in the universe that we can see, all the stars, all the galaxies, all the gas and the dust, all the luminous ordinary matter that we are made of, we find that it falls dramatically short. All the visible matter in the cosmos, all the baryonic matter that makes up the planets, the stars, and ourselves, accounts for only about 5% of the total critical density that is required to make the universe flat. The vast majority of the universe, about 95% of its total mass and energy content, is missing. The universe, it seems, is hiding its true nature from us. The shape of reality is not sculpted by the familiar shining matter of the stars. It is sculpted by something else, something dark, something invisible, something that we cannot see and cannot directly touch. Our quest to understand the shape of reality now becomes a ghost story, a search for the unseen and the unknown. The first of these great cosmic ghosts is a substance known as dark matter. The story of dark matter begins not in the modern era of precision cosmology, but in the 1930s, with the work of a brilliant and cantankerous Swiss-American astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a vast and distant swarm of over 1,000 galaxies, all bound together by their mutual gravity. He was trying to measure the total mass of the cluster. He did this in two different ways. First, he measured the total amount of light coming from all the galaxies in the cluster. From this, he could estimate the total number of stars and thus the total mass of the visible luminous matter. Then, he used a second independent method. He measured the orbital velocities of the individual galaxies as they moved around within the cluster. The galaxies were moving at incredibly high speeds, some at over 1,000 kilometers per second. For the cluster to remain gravitationally bound, for the galaxies not to simply fly apart, there had to be a huge amount of mass, a huge amount of gravity holding them all together. From the speeds of the galaxies, Zwicky could calculate the total mass that was required to keep the cluster from flying apart. And when he compared the two results, he found a stunning and inexplicable discrepancy. The mass that was required to hold the cluster together was over 400 times greater than the mass that he could account for from all the visible stars. The vast majority of the mass in the Coma Cluster was missing. It was invisible. Zwicky, with his characteristic bluntness, called this missing mass dunkel Materie, or dark matter. For decades, Zwicky's discovery was largely ignored by the astronomical community. His results were so strange, and his personality so abrasive, that many astronomers simply assumed that there must be some error in his observations or his calculations. The idea of a universe that was dominated by an invisible substance was simply too radical to be accepted. But then, in the 1970s, another brilliant and tenacious astronomer, Vera Rubin, would provide the second and ultimately undeniable piece of evidence for the existence of dark matter. Rubin was not looking at clusters of galaxies. She was studying the rotation of individual spiral galaxies, like our own Milky Way. She was measuring the rotation curve of the galaxies, a plot of the orbital speed of the stars versus their distance from the galactic center. The classical Newtonian physics that had worked so well for our own solar system made a clear prediction. In our solar system, most of the mass is concentrated in the center, in the Sun. As you move farther away from the Sun, the force of gravity gets weaker, and the orbital speeds of the planets decrease. Mercury moves much faster than Neptune. The same, it was assumed, should be true for a galaxy. Most of the visible matter, the stars and the gas, is concentrated in the bright central bulge. As you move out into the dimmer outer regions of the galaxy, the orbital speeds of the stars should decrease. But this is not what Vera Rubin found. In galaxy after galaxy, she found that the rotation curves were flat. The stars in the outer regions of the galaxies were moving just as fast as the stars in the inner regions. They were moving far too fast. For these outer stars to be held in their orbits, for them not to be flung out into the intergalactic void, there had to be a huge amount of extra unseen mass, exerting a powerful gravitational pull. Rubin's careful and systematic work showed that this was not an anomaly. It was a universal feature of spiral galaxies. The conclusion was inescapable. The visible shining disk of a galaxy, the part that we can see with our telescopes, is just the tip of the iceberg. It is a small, luminous component that is embedded in a much larger and completely invisible halo of dark matter. This dark matter halo is roughly spherical, and it extends far beyond the visible edge of the galaxy. It is this unseen scaffolding that provides the vast majority of the galaxy's mass, and that governs the motion of the stars within it. The evidence for dark matter has continued to grow, and it is now overwhelming. We see its effects in the way that the gravity of galaxy clusters can bend and distort the light from more distant objects, a phenomenon known as gravitational lensing. The amount of lensing we see is far greater than can be accounted for by the visible matter alone, and it allows us to create a map of the distribution of the unseen dark matter. We see its imprint in the temperature fluctuations of the cosmic microwave background, and we see its crucial role in the computer simulations that model the formation of the large-scale structure of the universe. Without dark matter, the universe as we know it, with its intricate web-like structure of galaxies and clusters, would not exist. The weak gravity of the ordinary visible matter would not have been strong enough to pull itself together into the structures we see today. Dark matter is the silent, invisible architect of the cosmos. So what is it? What is this mysterious, invisible substance that makes up about 27% of the total mass and energy of the universe, and about 85% of its total matter content? The honest answer is that we do not know, but we know a lot about what it is not. We know that it is not just ordinary baryonic matter that is simply not shining. It is not a vast collection of dead stars, black holes, or cold gas clouds. We can calculate from our understanding of the physics of the early universe, a process called Big Bang nuclear synthesis, the total amount of baryonic matter that should exist. And that amount is perfectly consistent with the 5% of the universe's critical density that we see in the visible matter. The dark matter must be something else, something new, something non-baryonic. We also know that dark matter is dark because it does not seem to interact with light in any way. It does not emit, absorb, or reflect light. It is, for all intents and purposes, completely transparent. This means that it does not interact through the electromagnetic force, and we know that it is cold, which in cosmological terms means that it was moving slowly in the early universe. This is what allowed it to clump together into the dense halos that provided the gravitational seeds for the formation of galaxies. The leading candidate for what dark matter might be is a new, undiscovered type of subatomic particle. This hypothetical particle is often called a WIMP, which stands for weakly interacting massive particle. A WIMP would be a heavy particle, which would explain its strong gravitational influence, and it would interact with other particles only through the weak nuclear force and through gravity, which would explain why it is so difficult to detect. It would be a ghost particle, a particle that can pass through ordinary matter, through the Earth, and through our own bodies, as if we were not even here. All over the world, physicists are engaged in a great and difficult hunt for this elusive particle. There are three main strategies. The first is to try to create dark matter particles in powerful particle accelerators, like the Large Hadron Collider at CERN. The second is to try to detect them directly, here on Earth. This involves building incredibly sensitive detectors, deep underground, shielded from all other forms of radiation, in the hope of catching the rare and fleeting signal of a single WIMP particle, bumping into an atomic nucleus. The third strategy is to try to detect them indirectly, by looking for the products of their annihilation. If two WIMP particles were to meet, they should annihilate each other in a flash of high-energy gamma rays, which we could then detect with our telescopes. So far, all of these searches have come up empty. The ghost continues to elude us. To contemplate the mystery of dark matter is to be confronted with the profound and humbling reality of our own ignorance. It is to realize that the universe we see, the beautiful, luminous world of the stars and the galaxies, is just a small, decorative froth on the surface of a much deeper, darker, and more mysterious cosmic ocean. The true shape of reality, the grand cosmic architecture of the universe, is built out of a substance that we cannot see, that we do not understand, and that may forever remain beyond the reach of our direct experience. We are living in a ghost world, a world that is shaped and governed by the silent, invisible, and ever-present hand of the dark. Our cosmic census has so far revealed a strange and mysterious universe. We have learned that the familiar baryonic matter that makes up everything we can see accounts for only a tiny 5% fraction of the total mass and energy required to explain the flat geometry of our cosmos. We have discovered the existence of a vast unseen scaffolding of dark matter, a mysterious, non-baryonic substance that accounts for another 27% of the cosmic budget. But even when we add these two together, we are still left with a profound and gaping deficit. About 68% of the universe The vast majority of its substance is still missing. The search for this final missing piece of the cosmic puzzle would lead to one of the most shocking, most profound, and most revolutionary discoveries in the history of science. It would lead to the discovery of a strange, new, and enigmatic entity that is pushing our universe apart. It would lead to the discovery of dark energy. The story of dark energy begins in the late 1990s with two independent teams of astronomers who were engaged in a great cosmic quest. They were trying to measure the ultimate fate of the universe. For decades, the central question in cosmology had been whether the universe would expand forever, or whether the collective gravity of all the matter it contained would eventually halt the expansion and cause it to recollapse in a big crunch. The answer depended on the density of the universe, on how much stuff there was to pull it all back together. The astronomers were trying to answer this question by measuring the rate at which the expansion of the universe was slowing down. To do this, they needed to measure the distances to, and the recession velocities of, very distant objects. They needed to look deep into the past to see what the expansion rate of the universe was billions of years ago, and to compare it to the expansion rate today. The standard candles they chose for this task were a special and very powerful type of stellar explosion known as a Type Ia supernova. A Type Ia supernova is the explosion of a white dwarf star that has been accreting matter from a companion star. Because these explosions always happen when the white dwarf reaches a specific critical mass, the Chandrasekhar limit, they all have almost exactly the same intrinsic brightness. They are like cosmic light bulbs of a standard 100-watt wattage. By measuring the apparent brightness of a distant Type Ia supernova, astronomers can calculate its distance with great precision, and by measuring the redshift of its light, they can measure how fast it is moving away from us. The two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, spent years painstakingly searching for these faint, distant explosions and measuring their properties. They expected to find that the expansion of the universe was slowing down. The only question was by how much. But when they analysed their data, they found something completely and utterly astonishing. The distant supernovae were dimmer than they should have been. They were farther away than their redshifts would have suggested. This meant that in the past the universe was expanding more slowly than it is today. The expansion of the universe is not slowing down. It is speeding up. It is accelerating. This was a discovery that shook the very foundations of cosmology. It was so unexpected, so contrary to all of the prevailing theories, that the astronomers themselves were initially convinced that it must be a mistake. They spent months checking and rechecking their data, searching for any possible source of error. But the result was robust. Both teams, using different methods and different supernovae, had come to the same shocking conclusion. The universe is accelerating. In 2011, the leaders of these two teams were awarded the Nobel Prize in Physics for their revolutionary discovery. But what could be causing this cosmic acceleration? The force of gravity as we know it is always attractive. It should be pulling the universe together, slowing the expansion down. To cause the expansion to accelerate, there must be some kind of new, strange and mysterious energy, a kind of anti-gravity that is inherent in the very fabric of space itself, that is pushing the universe apart. This mysterious repulsive energy was given the name dark energy. When the cosmologists calculated how much of this dark energy would be required to explain the observed acceleration, they found that it accounted for, almost perfectly, the missing 68% of the universe's critical density. The cosmic budget was finally balanced. The flat geometry of the universe was explained. The universe is flat because its total density is made up of 5% ordinary matter, 27% dark matter, and 68% dark energy. So what is this dark energy? As with dark matter, the honest answer is that we do not know. It is perhaps the single greatest mystery in all of science. But there is a leading and deeply strange candidate. The leading candidate for dark energy is a concept that was first proposed and then famously discarded by Albert Einstein himself. When Einstein was first developing his general theory of relativity, he was working under the prevailing assumption that the universe was static and eternal. But he found that his own equations predicted a dynamic universe, a universe that should be either expanding or contracting. To fix this problem, to force his equations to produce a static universe, he added an extra term, a fudge factor, which he called the cosmological constant. This cosmological constant represented a constant uniform energy density that was inherent in the fabric of empty space itself, a kind of intrinsic energy of the void. This energy would have a strange, repulsive anti-gravitational effect, which could be used to perfectly balance the attractive force of gravity and to produce a static universe. But then, in the 1920s, the astronomer Edwin Hubble discovered that the universe was not static. It was expanding. Einstein's original equations had been right all along. He had no need for his fudge factor. He later called the cosmological constant his greatest blunder. But now, in a strange and ironic twist of scientific history, Einstein's greatest blunder has returned with a vengeance as our leading explanation for dark energy. The cosmic acceleration seems to be telling us that there really is a small but non-zero energy density inherent in the vacuum of empty space. This vacuum energy would have exactly the right, repulsive properties to drive the universe's accelerated expansion. But this idea comes with its own, enormous, and deeply troubling problem. When the physicists of the quantum world try to calculate how much of this vacuum energy there should be, based on our understanding of the quantum fluctuations of virtual particles that are constantly popping in and out of existence in the empty void, they get a number that is catastrophically, comically wrong. The theoretical prediction for the amount of vacuum energy is about 10 to the power of 120 times larger than the amount that we actually observe. This is the largest and most embarrassing discrepancy between theory and observation in the entire history of science. It is known as the cosmological constant problem, and it is a profound sign that we are missing something very, very fundamental in our understanding of the relationship between gravity and the quantum world. The discovery of dark energy has completely changed our picture of the ultimate fate of the universe. In a universe that is dominated by matter, the expansion will always slow down. But in a universe that is dominated by dark energy, the future is one of perpetual and ever-increasing acceleration. As the universe expands, the density of the ordinary matter and the dark matter will decrease as they are spread out over a larger and larger volume. But the density of the dark energy, if it is a true cosmological constant, will remain constant. It is an intrinsic property of space itself. So as more space is created, more dark energy is created along with it. This means that as time goes on, the dark energy will become more and more dominant. The acceleration will get stronger and stronger. The galaxies will be pushed apart from each other at an ever-increasing rate. In the far distant future, all of the other galaxies in the universe, the galaxies that are not gravitationally bound to our own local group, will be pushed beyond our cosmic horizon. They will recede from us faster than the speed of light, and their light will never be able to reach us again. The night sky of a future, far distant observer will be a dark, lonely and empty place, containing only the stars of our own, merged Milky Way galaxy. The rest of the universe will have been erased from view, and the acceleration may not stop there. In one, highly speculative but terrifying scenario known as the Big Rip, the repulsive force of the dark energy could become so strong that it would eventually overcome all the other forces of nature. It would first tear apart the great clusters of galaxies, then the galaxies themselves, then the solar systems, then the stars and the planets, then the atoms, and finally the atomic nuclei themselves, ripping the very fabric of reality into its constituent fundamental particles. To contemplate the enigma of dark energy is to be confronted with the profound and humbling strangeness of our cosmic home. It is to realize that the shape of our reality is not just sculpted by the familiar, attractive force of gravity, but is also being driven by a mysterious, repulsive, and dominant force that is inherent in the emptiness of the void itself. It is to understand that we are living in a runaway universe, a universe that is becoming emptier, colder, and lonelier with every passing moment. The ultimate fate of our reality is not a fiery crunch, but a long, cold, and accelerating journey into an endless and ever-darkening night. Our journey to understand the shape of reality has taken us to the grandest cosmic scales, to the very edge of the observable universe, and into the profound mysteries of the dark substances that govern its fate. Now let us return from these vast expansive vistas and journey to a single, specific, and terrifyingly compact location, Let us travel to a place where the elegant geometric fabric of Einstein's spacetime is stretched to its absolute breaking point, a place where the curvature becomes infinite and the laws of physics as we know them cease to have any meaning. This is the ultimate gravity well, the bottomless pit in the cosmic landscape. This is the black hole, a true and literal puncture in the fabric of reality. The story of the black hole begins, like so many stories in modern physics, as a strange and unsettling prediction of Einstein's general theory of relativity. Just a few months after Einstein published his theory in 1915, the German physicist and astronomer Karl Schwarzschild, while serving on the front lines of World War I, found the first exact mathematical solution to Einstein's complex equations. Schwarzschild's solution described the geometry of space-time around a single, spherical, non-rotating mass, like a star or a planet. His solution perfectly described the gentle curvature of the gravity wells that hold the planets in their orbits. But it also contained a bizarre and deeply disturbing feature. Schwarzschild's mathematics showed that if you could compress any given mass into a sufficiently small volume, a critical radius now known as the Schwarzschild radius, something dramatic and catastrophic would happen. The curvature of space-time at this radius would become so extreme that it would, in a sense, fold in on itself, creating a one-way membrane, a surface of no return. The escape velocity from this surface would be equal to the speed of light. Anything that crossed this boundary, even a particle of light, could never escape. It would be trapped forever by the immense gravity. The object would become, for all intents and purposes, invisible, a black hole in the fabric of the cosmos. Even more strangely, Schwarzschild's solution predicted that at the very centre of this object, the curvature of space-time and the density of matter would become infinite. It predicted a singularity, a point of zero volume and infinite density, a place where the elegant mathematics of general relativity breaks down into nonsensical infinities. For decades, this strange mathematical prediction was regarded by most physicists, including Einstein himself, as a mathematical curiosity, a bizarre artifact of the equations that could not possibly correspond to anything in the real physical world. The universe, it was assumed, would surely have some way of preventing the formation of such a monstrous and paradoxical object. But the universe, it turns out, is stranger than we thought. In the 1930s, the brilliant young Indian physicist Subrahmanyan Chandrasekhar, during a long sea voyage from India to England, made a remarkable calculation. He applied the new laws of quantum mechanics and special relativity to the physics of stars. He showed that for a certain kind of dead star, a white dwarf, there is a maximum possible mass, about 1.4 times the mass of our Sun. If a white dwarf were to exceed this mass, the quantum pressure of its electrons, the force that was holding it up against the crush of its own gravity, would fail. The star would be forced to collapse, catastrophically, into something denser. A few years later, the physicists Robert Oppenheimer and Hartland Snyder took the next step. They asked what would happen to a very massive star, a star much more massive than our Sun, when it runs out of fuel at the end of its life. The star's outer layers would explode in a brilliant supernova, but its dense, central core would collapse under its own immense gravity. Oppenheimer and Snyder's calculations showed that if the collapsing core was more than about 3 times the mass of the Sun, there was no known force in the universe that could stop the collapse. The core would not just collapse into a white dwarf or even into a super-dense neutron star. It would just keep collapsing, forever, crushing itself down past its Schwarzschild radius, and beyond, all the way down to the infinite density of a singularity. The black hole was not just a mathematical curiosity. It was an inevitable prediction of the laws of physics. It was the natural and unavoidable tomb of the most massive stars in the universe. To contemplate a black hole is to contemplate the ultimate expression of the curvature of space-time. Let us imagine a journey towards one. From a great distance, the black hole is just a source of gravity, no different from a star of the same mass. But as we get closer, the strange effects of the extreme geometry become apparent. The gravity well becomes incredibly steep. The fabric of space-time is being pulled into the black hole, like water flowing towards a drain. As we approach the event horizon, the surface of no return, the effects of gravitational time dilation become extreme. To a distant observer, our clock would appear to be ticking, slower and slower. Our journey towards the horizon would seem to take an infinite amount of time. They would see our image become frozen and then fade away as the light from our spaceship becomes infinitely redshifted. From their perspective, we would never actually cross the event horizon. But from our own personal perspective, our journey would be finite. We would feel the powerful tidal forces of the black hole, the spaghettification that would stretch our body in the vertical direction and squeeze it in the horizontal direction. And then, in a finite and final moment, we would cross the event horizon. This moment would be, in a strange way, completely unremarkable. The event horizon is not a physical surface. It is a purely geometric boundary in space-time. There is no wall, no signpost. We would simply drift across it, unaware that we had just passed the point of no return, but our fate would now be sealed. Once inside the event horizon, the shape of reality is profoundly and terrifyingly altered. The roles of space and time are, in a sense, interchanged. Outside the black hole, we are free to move in any direction in space, but we are forced to move, inexorably, forward in time. Inside the black hole, this is reversed. The singularity is no longer a place in space, it is a moment in the future. All possible paths, all possible trajectories now lead only in one direction, towards the central singularity. The flow of space-time itself has become a one-way conveyor belt, and it is carrying us, inevitably, to our doom. The future of anything that crosses the event horizon is the singularity. The singularity itself is the place where our current understanding of reality comes to a complete and total end. It is a point where the curvature of space-time is infinite, where the laws of general relativity break down. It is a place where the smooth, geometric fabric of Einstein's universe is torn apart. To truly understand what happens at the singularity, we would need a new theory, a theory that can unite the laws of gravity with the laws of the quantum world, a theory of quantum gravity. This is the great unfinished quest of modern physics. But the mysteries of the black hole do not end at the singularity. In the 1970s, the physicist Stephen Hawking made a discovery that was almost as revolutionary as the black hole itself. By applying the principles of quantum mechanics to the region just outside the event horizon, Hawking showed that black holes are not, in fact, completely black. They should glow, ever so faintly, with a thermal radiation, a phenomenon now known as Hawking radiation. The quantum vacuum of empty space is a bubbling, seething foam of virtual particles that are constantly popping into existence in a particle-antiparticle pairs and then annihilating each other a moment later. Hawking realized that if a pair of these virtual particles were to be created right at the edge of the event horizon, it is possible for one of them to be created right at the edge of the event horizon, them to fall into the black hole while the other one escapes. The escaping particle becomes a real particle, a particle of Hawking radiation. To an outside observer, it looks as if the black hole is emitting particles. This radiation has a profound consequence. The energy for the escaping particle has to come from somewhere. It comes from the mass of the black hole itself. This means that a black hole is not an eternal prison. It can evaporate. The process is incredibly, unimaginably slow for a large stellar mass black hole. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate a single atom. But over vast, almost infinite timescales, a black hole will slowly radiate away its mass, getting smaller, hotter, and radiating faster until it finally disappears in a final brilliant flash of gamma rays. This evaporation leads to the deepest and most profound paradox in all of modern physics, the black hole information paradox. One of the fundamental principles of quantum mechanics is that information can never be destroyed. The total amount of information in the universe is always conserved. But what happens to the information about all the things that fell into the black hole? When the black hole evaporates, it seems to emit only a random thermal radiation, which contains no information about what went into making it. The information seems to be lost forever. This is a direct and profound contradiction between the laws of general relativity and the laws of quantum mechanics. To contemplate the black hole is to stand at the very precipice of our human understanding. It is a place where space and time become warped and twisted into unrecognizable shapes. It is a place where the two great pillars of modern physics, relativity and quantum mechanics, collide in a spectacular and paradoxical conflict. The black hole is not just an object in the universe. It is a gateway to a new and deeper level of reality, a reality that is still waiting to be discovered. It is a puncture in the familiar fabric of our world, and through that puncture we can catch a terrifying and tantalizing glimpse of the true and still unknown shape of everything. Our journey into the shape of reality has led us to the black hole, a place of ultimate mystery, a place where the smooth fabric of space-time is torn apart and the two great pillars of modern physics, general relativity and quantum mechanics, clash in a profound and unresolved paradox. The black hole information paradox, the apparent destruction of quantum information in the process of Hawking evaporation, has been the driving force behind some of the most radical and mind-bending ideas in theoretical physics for the past 50 years. And out of this deep and troubling conflict, a new and astonishing principle has emerged, a principle that suggests that our perception of reality, our experience of a three-dimensional world, may be a profound and beautiful illusion. This is the holographic principle. The story of the holographic principle begins with a simple question. Where is the information in a black hole stored? In the classical world, the amount of information that can be stored in a volume of space is proportional to the volume itself. If you have a box, you can store more information in it by making the box bigger, or by packing the information more densely within it. But a black hole seems to be different. In the 1970s, the physicist Jacob Bekenstein was contemplating the entropy of a black hole. In thermodynamics, entropy is a measure of the disorder or the hidden information of a system. Bekenstein argued that a black hole must have entropy. If you throw something with a lot of entropy, like a hot cup of coffee, into a black hole, its entropy seems to disappear from the universe, which would violate the second law of thermodynamics. To save the second law, the black hole itself must have an entropy that increases by at least the amount of the entropy that was thrown in. Bekenstein then made a remarkable discovery. He found that the entropy of a black hole, the total amount of information it can contain, is not proportional to its volume. It is proportional to the surface area of its event horizon. This was a bizarre and revolutionary idea. It was as if all the information about the three-dimensional interior of the black hole, all the information about all the stars, the planets, and the cups of coffee that had ever fallen into it, was somehow encoded, not within its volume, but on its two-dimensional boundary surface. The amount of information that could be stored in the most information-dense object in the universe was limited by its surface area, not its volume. A few years later, Stephen Hawking's discovery of Hawking radiation confirmed Bekenstein's idea and provided an exact formula for the entropy of a black hole. The Bekenstein-Hawking formula is one of the most beautiful and mysterious equations in all of physics. It connects the geometry of space-time, the surface area of the event horizon, the principles of quantum mechanics, Planck's constant, and the laws of thermodynamics, the entropy, and it confirms that the information content of a black hole is a property of its surface. This strange result that the information in a volume is encoded on its boundary lay dormant for many years. But in the 1990s, two of the leading thinkers in theoretical physics, Gerard 't Hooft and Leonard Susskind, took this idea and elevated it to a grand cosmic principle. They proposed that this strange property of black holes might not be a special feature of black holes at all. It might be a fundamental principle of the universe itself. This is the holographic principle. The holographic principle states that the description of a volume of space can be thought of as being encoded on a lower dimensional boundary to that region. In its strongest form, it suggests that our entire three-dimensional universe, everything we see and experience, might be a holographic projection of information that is stored on a distant two-dimensional surface at the very edge of the cosmos. Let us try to understand this with the analogy of a security hologram on a credit card. A hologram is a two-dimensional flat piece of plastic, but when you look at it, you see a three-dimensional image. The image has depth, it has parallax, it looks real. But all of the information that is required to create that three-dimensional image is fully encoded in the intricate microscopic interference pattern that is stored on the two-dimensional surface of the film. The holographic principle suggests that our universe might be like this. The three-dimensional world that we experience, with its depth, its solidity, and its familiar laws of physics, may be the image. The real underlying reality may be a flat two-dimensional film at the boundary of space-time, upon which the fundamental laws of physics are written in a completely different and much simpler language. The world we see is a projection, a hologram. This idea, as fantastical as it sounds, is not just a wild philosophical speculation. It has a firm mathematical foundation in the strange and powerful world of string theory, our leading candidate for a theory of quantum gravity. In 1997, the physicist Juan Maldacena made a groundbreaking discovery that gave a concrete mathematical realization of the holographic principle. He discovered a profound and unexpected duality, a kind of mathematical dictionary that connects two, seemingly completely different, physical theories. On one side of the duality, there is a theory of gravity, a theory that lives in a five-dimensional curved spacetime known as anti-de Sitter space. This is the bulk theory. On the other side of the duality, there is a quantum field theory, a theory of interacting particles that does not include gravity, which lives on the flat four-dimensional boundary of that spacetime. This is the boundary theory. Maldacena showed that these two completely different theories are, in fact, mathematically equivalent. They are two different descriptions of the exact same underlying reality. Anything that happens in the five-dimensional gravitational world of the bulk can be perfectly described by a corresponding process in the four-dimensional, non-gravitational world of the boundary, and vice versa. The five-dimensional universe with gravity is a holographic projection of the four-dimensional universe without gravity. This ADS/CFT correspondence is one of the most powerful and important discoveries in modern theoretical physics. It provides a concrete working model of the holographic principle, and it gives us a powerful new tool for understanding the deepest and most difficult problems in physics. It allows us to translate a hard, intractable problem in one theory into a simpler, more manageable problem in the other dual theory. For example, it may allow us to understand the profound mysteries of quantum gravity in the bulk by studying the much simpler and better understood quantum field theory on the boundary. So, what does this mean for the shape of our reality? Does the holographic principle mean that our world is not real? Does it mean that we are living in a simulation? Not exactly. The holographic image on a credit card is an illusion, but in the holographic principle, both the bulk and the boundary descriptions are considered to be equally real. They are just two different languages that are being used to describe the same, underlying physical reality. We experience the world as a three-dimensional place with gravity, but there may be another, equally valid way to describe our world as a two-dimensional place without gravity. The holographic principle suggests that the fundamental degrees of freedom of the universe, the pixels of reality, may live not in the volume of space but on its boundary, and it suggests that the most fundamental and mysterious force in the universe, gravity, may not be fundamental at all. It may be an emergent phenomenon, a macroscopic illusion that arises from the quantum interactions of the particles that live on the distant boundary surface. In the holographic picture, gravity is a kind of thermodynamic statistical effect, an echo of the quantum world. To contemplate the holographic principle is to be confronted with the ultimate mind-bending strangeness of the shape of reality. It is to entertain the possibility that the solid, three-dimensional world of our experience is a grand and beautiful projection of a simpler, flatter, and more fundamental reality. It is to see that the space and the dimensions that we take for granted may not be fundamental properties of the universe, but emergent illusions. The shape of reality may not be a shape at all in the way that we understand it. It may be a pattern, an interference, a piece of information written on a distant cosmic screen. The universe is not a place, it is a message, and we are living inside the hologram. Our journey into the shape of reality has led us to a profound and unsettling crisis. We have two magnificent and spectacularly successful theories that describe our universe. We have general relativity, Einstein's beautiful geometric theory of the large, which describes the smooth, curved fabric of space-time and the force of gravity. And we have quantum mechanics, the strange and powerful theory of the small, which describes the pixelated, probabilistic and interconnected world of particles and forces. Both of these theories have been tested and verified with incredible precision in their own respective domains. But when we try to bring them together, when we try to describe a situation where the very large meets the very small, such as in the fiery heart of the Big Bang or at the infinite central singularity of a black hole, they clash. They produce a cacophony of nonsensical infinities. The two great pillars of modern physics are fundamentally incompatible. For over half a century, the quest to resolve this deep and profound conflict, the search for a single, unified theory of quantum gravity that can seamlessly describe both the cosmic and the quantum, has been the holy grail of theoretical physics, and the most ambitious, the most mathematically elegant, and the most tantalizingly beautiful candidate for such a theory is a radical and revolutionary idea that reimagines the very substance of the world. It is an idea that suggests that the fundamental constituents of reality are not point-like particles at all, but something far stranger and more musical. This is the world of string theory, a universe that is not made of points, but of a symphony of tiny, vibrating strings. Let us, in our minds, zoom in on a single, fundamental particle, an electron. In the standard model of particle physics, which is our current quantum mechanical description of the subatomic world, the electron is a point. It has no size, no volume, no internal structure. It is a zero-dimensional mathematical point that is endowed with certain intrinsic properties, like mass and charge. This picture has been incredibly successful, but it is also the source of many of the deep mathematical problems that plague our theories, particularly the infinities that arise when we try to calculate the interactions of these points at zero distance. String theory proposes a simple and profound solution to this problem. It suggests that if we could zoom in on that electron with an unimaginable and perhaps impossible degree of magnification, we would see that it is not a point at all. We would see that it is, in fact, a tiny one-dimensional vibrating loop of energy, a string. This string is incredibly, unimaginably small, on the order of the Planck length, about 10 to the power of negative 35 meters, a scale that is as small compared to an atom as an atom is compared to our entire solar system. From our macroscopic low-resolution perspective, this tiny, vibrating loop looks just like a point-like particle, in the same way that a distant vibrating guitar string looks like a simple, stationary line. This single, simple and elegant modification, replacing the zero-dimensional point with a one-dimensional string, has profound and far-reaching consequences. It immediately smooths out the problematic point-like interactions of quantum field theory. Because the strings have a finite, albeit tiny extension in space, they do not interact at a single, zero-dimensional point. They interact over a small, smeared-out region of spacetime. This smearing has the effect of taming the wild infinities that have plagued our attempts to unify gravity with the other forces. The universe, at its most fundamental level, is not sharp and pointy. It is soft and fuzzy. But the true beauty and power of string theory lies in its musical analogy. A violin string can vibrate in many different ways. It can vibrate at its fundamental frequency, producing a low note, or it can vibrate in a variety of different harmonics or overtones, producing a series of higher, clearer notes. The different vibrational modes of the string give rise to the different musical notes that we can hear. String theory proposes that the same is true for the fundamental strings of reality. The different, elementary particles that we observe in our universe are nothing more than the different vibrational modes of these tiny, fundamental strings. An electron is a string that is vibrating in one particular pattern. A photon is a string that is vibrating in another different pattern. A quark is a string that is vibrating in yet another pattern. The entire rich and complex particle zoo of the Standard Model, with its dozens of different seemingly fundamental particles, is revealed to be just the different notes of a single, underlying and universal entity. The universe is a cosmic symphony. The properties of each particle, its mass, its charge, its spin, are determined by the specific way in which its underlying string is vibrating. The mass of a particle is related to the energy of the string's vibration through Einstein's famous equation E equals mc squared. A more energetic vibration corresponds to a more massive particle. The charge of a particle is related to the way the string interacts with the background, electromagnetic field. The universe of particles is no longer a random collection of different fundamental building blocks. It is a unified, elegant, and deeply musical system. And here is the most remarkable and beautiful prediction of the theory. Among the infinite number of possible vibrational modes of the string, there is one particular mode that has a very special set of properties. It is a massless particle with a spin of 2. When the physicists calculated the properties of this hypothetical particle, they found that they were identical to the properties of the graviton, the long-sought-after hypothetical quantum particle of gravity. This is the great triumph of string theory. Gravity is not something that needs to be added to the theory by hand. It is an inevitable and unavoidable consequence of the theory itself. The existence of gravity is a prediction of string theory, the same fundamental entity, the vibrating string, that can describe the particles of matter, like electrons and quarks, and the particles of the other forces, like photons, can also describe the particle of gravity. For the first time, we have a single, unified framework that can, in principle, describe all of the known forces and all of the known particles of nature. It is a true theory of everything. But this beautiful and ambitious theory is not without its own profound challenges and its own deep mysteries. String theory is not a single theory, but a vast and complex landscape of different related theories, and it makes a series of strange and radical predictions about the shape of reality that are at present impossible to test experimentally. The most famous and most challenging of these predictions is that the universe is not, in fact, four-dimensional. For the mathematics of string theory to be consistent, for it to be free of paradoxes and anomalies, it requires that the universe must have more dimensions than the three of space and the one of time that we experience. The original, bosonic string theory required a universe with 26 dimensions. The more modern and more realistic superstring theories, which incorporate a key symmetry known as supersymmetry, require a universe with 10 dimensions, 9 of space and 1 of time. This leads to an immediate and obvious question. If the universe really has 10 dimensions, where are the other 6? Why do we only experience a 3-dimensional world? The answer, as we will explore in our next chapter, is that these extra dimensions may be hidden from us, curled up into a tiny, complex and beautiful geometric shape at every single point in our familiar 4-dimensional reality. To contemplate the world of string theory is to embrace a new and deeply musical vision of the shape of reality. It is to see that the fundamental constituents of the universe are not hard, dead, point-like particles, but vibrant, energetic and musical loops of energy. It is to hear the rich and complex world of the particle zoo as the different notes and harmonies of a single cosmic instrument, and it is to accept that the ultimate unifying theory of the cosmos may not be a theory of things at all, but a theory of vibrations, a theory of music, a theory of the beautiful, silent and universal symphony of the strings of creation. The beautiful and ambitious framework of string theory has offered us a tantalizing vision of a unified reality, a universe where all the particles and all the forces are just the different, musical notes of a single, vibrating, fundamental string. But this elegant musical vision comes at a strange and seemingly impossible price. For the mathematics of the theory to be consistent, the universe cannot have only the 4 familiar dimensions of space-time, 3 of space and 1 of time, that we experience in our everyday lives. The theory demands that the universe must have more dimensions. The most promising versions of the theory, the superstring theories, require a universe with a total of 10 dimensions. This is perhaps the most radical and most counterintuitive prediction in the entire history of science. If the universe truly has 10 dimensions, then where are the other 6? The answer that string theory provides is as elegant as it is strange. The extra dimensions are not missing, they are simply hidden. They are hidden from our large macroscopic senses because they are incredibly, unimaginably small. At every single point in our familiar, 4-dimensional space-time, the theory suggests, there exists another 6-dimensional space that is compactified, or curled up, into a tiny, intricate and complex geometric shape. Let us try to visualize this with a simple, 2-dimensional analogy. Imagine a long, thin garden hose. From a great distance, the hose looks like a simple, 1-dimensional line. An ant walking along the hose can only move in one direction, forward or backward. But if we look at the hose up close, we see that it is not 1-dimensional at all. At every point along the length of the hose, there is another small circular dimension, the circumference of the hose. The ant can walk along the long, extended dimension of the hose, but it can also walk around the small, curled-up circular dimension. The hose is a 2-dimensional surface, but one of its dimensions is large and extended, and the other one is small and compact. String theory proposes that our universe is like this, but on a much grander and more complex scale. The three spatial dimensions that we experience are the large extended dimensions, like the length of the hose, but at every single point in this three-dimensional space, there is another six-dimensional shape that is curled up so tightly, on a scale that is even smaller than an atom, that we are completely unaware of its existence. We are like the distant observer who sees the hose only as a one-dimensional line. We are too large to perceive the tiny, curled-up dimensions. Only a fundamental string, an entity that is as small as the curled-up dimensions themselves, can see and move in this hidden six-dimensional space. This idea of extra curled-up dimensions is not, in fact, a new one. It was first proposed in the 1920s by the physicists Theodor Kaluza and Oscar Klein, in an early and brilliant attempt to unify the forces of gravity and electromagnetism. They showed that if you start with Einstein's theory of gravity in a five-dimensional universe, and you then curl up the fifth dimension into a tiny circle, the theory that emerges in the remaining four dimensions looks almost exactly like Einstein's original theory of gravity, plus Maxwell's theory of electromagnetism. The force of electromagnetism in this picture is a manifestation of the geometry of the hidden fifth dimension. It was a beautiful and tantalizing idea, but it was ultimately incomplete. String theory has revived and expanded this idea in a profound and powerful way. The extra six dimensions of string theory are not just a simple circle. For the theory to be consistent and for it to reproduce the known laws of physics in our four-dimensional world, these six dimensions must be curled up into a very special and very complex kind of geometric shape. These shapes are known as Calabi-Yau manifolds. A Calabi-Yau manifold is a complex six-dimensional geometric space that is breathtakingly intricate and beautiful. They are a rich and fascinating subject of study in their own right, at the very frontiers of pure mathematics. There are tens of thousands, perhaps even an infinite number, of different possible Calabi-Yau shapes, and this leads to one of the greatest and most profound challenges of string theory. The precise shape of the hidden Calabi-Yau manifold is not just a mathematical detail, it is everything. The geometry of this tiny curled-up space, its size, its shape, the number of holes it has, the way it is twisted and connected, determines the fundamental laws of physics that we experience in our large four-dimensional world. The different vibrational modes of the fundamental strings are determined by the geometry of the Calabi-Yau space in which they are vibrating. The different notes of the cosmic symphony are determined by the shape of the instrument on which they are being played. The masses of the different particles, the strengths of the different forces, the number of different particle families, all of the fundamental physical constants of our universe that we have so carefully measured are, in this picture, not fundamental at all. They are just the consequences of the specific geometric properties of the hidden Calabi-Yau manifold that exist at every point in our reality. If the hidden dimensions had a different shape, the laws of physics would be different. The universe would be a different place. This is a beautiful and powerful idea. It suggests that all the seemingly arbitrary numbers that define our reality might be, in the end, just the result of a single, underlying geometric structure. The physics of our universe is a consequence of the geometry of its hidden dimensions, but it also presents a profound problem. String theory does not, at present, tell us which of the tens of thousands of possible Calabi-Yau shapes is the right one for our universe. The theory seems to allow for a vast and sprawling landscape of different, possible universes, each one corresponding to a different way of curling up the extra dimensions, and each one with its own unique set of physical laws. Why did our universe choose this particular shape and not another? Why do we live in a universe with these specific laws, and not one of the countless other possible sets of laws? This landscape problem is one of the most active and most controversial areas of research in modern theoretical physics. Some physicists believe that there must be some, as yet undiscovered, principle within string theory that will eventually allow us to select the one, unique Calabi-Yau shape that corresponds to our universe. Others have embraced a more radical and more philosophical perspective. They suggest that perhaps all of the possible shapes and all of the possible universes are equally real. This is the idea of the string theory multiverse. In this view, our universe, with its specific life-permitting laws of physics, is just one rare and fortunate pocket in a much larger cosmic landscape of countless other universes, each with its own, different, and likely life-prohibiting laws. We live in this universe simply because it is one of the few universes in which we could live, a concept known as the anthropic principle. To contemplate the hidden dimensions of string theory is to be confronted with a vision of reality that is almost beyond our ability to imagine. It is to accept that the world we see is just a four-dimensional shadow of a much richer, 10-dimensional reality. It is to see that at every single point in the space around us, there exists a tiny, intricate, and beautiful 6-dimensional geometric jewel, a Calabi-Yau manifold. And it is to understand that the shape of this hidden, microscopic jewel is the ultimate source of the laws that govern our macroscopic world. The shape of our reality is not just the grand cosmic curvature of the universe as a whole, it is also the tiny, intricate, and deeply mysterious geometry of the curled-up hidden world that lies, forever, beyond the reach of our senses.